So in this lecture, I don't want to talk much, okay? So I just want to explain a little bit about this graph more, okay? So one of the mistakes that I get in my previous explanation, it was that in the previous explanation, I mentioned that the overdamped system, they get close, but they never reach to the destination, okay? So this one is not full of the story. Sometimes the overdamped system, they don't even get close, okay? They would be far away, okay? So this one was some mistake that I did in my explanations. Or so it is like some sort of like friction or something like that. So in this one, I was drawing. So for example, what will happen is that this is the line that you want to go. You don't get even close to the guy, right? This is if this one is critically damped, okay? So your overdamped system, for example, it does not get even close. This is like, for example, there is too much friction or your power is not enough and this kind of thing. So this one is definitely a mistake that I get for you. And the second thing that is, this one also is for layman's, okay? So it is not for advanced people. So I don't want to go through pole zero placement. And for example, if you are close to the imaginary axis, or for example, this kind of thing. In here, this one is real axis, this one is the imaginary axis, okay? So what will happen? Okay, so for example, when he is on the imaginary axis, this one is too advanced already. Okay, so on the imaginary axis, you get an oscillator. If you go on the right, you will become unstable. On the left of the imaginary axis, you are stable. Okay, so you may have even, for example, bad oscillation, but you are stable. You will never die. Okay? So this is all this graph is all about. Okay, so find your imaginary axis. What will happen on your left? What will happen on your right? If you are on a real axis, if you go up, for you go far from the real axis, what will happen if you go? So this kind of things, he is explaining this, and this is a very good way to visualize the thing. But if I really suggest you to watch his video, okay, this is one of the best video to understand what's going on. One last thing that I forgot about this graph to mention when I was recording it. It was about the frequency of the oscillation. So although I mentioned about the stability and those kind of things, I forgot about to mention about the frequency. As you can see, okay, the nearer the thing it is, it means that you go down near the real axis. This one is the real axis, right? So you see the frequency, it is lower frequency, okay? And when you go higher, okay, when you go above the frequency that you see, it is how to say that it is higher. So this one, it is very important. Okay, why it is important? High frequency is easy to filter, okay, but low frequency is there. Especially, for example, imagine you have a motion, okay. So for example, the movement that you do, for example, each movement it take place every 10 millisecond or every 100 milliseconds, something like that. And the oscillation that you have is 10 hertz. It is if for example the issue is that the frequency of these two, they will collide on top of each other, so making it impossible to filter. But however, for example, imagine you have 10 hertz movement, okay, so even that every second you move 10 times, okay, so something very common in, for example, something like semicon, okay. But for example, your frequency, your noise frequency, or for example whatever, that if you have your PID, for example, the vibration that it has is at 2000 hertz, okay, 2 kilohertz, okay. This is very easy to filter, you know. So let's say you can use a low pass filter, you have a lot of options. But when you have some sort of a slow oscillation, yeah, it is impossible. So to just summarize the thing, so what does it mean? Okay, what you ideally want? You want to be as left as possible. When you are as left as possible, you would be having the fastest response. Okay, you see from something like this, and for example something like this, right? So when it is more over toward it on the right side of the track, okay, what you would see that it is you have more oscillation, and when you are toward left, you don't have oscillation at all. So but however, something like this, for example, imagine if it's, for example, no oscillation at all, this kind of thing, if it's on the real axis, it is impossible to achieve. So normally, for example, again, what you aim for is something like this, even that you have a small oscillation, okay, so but it die fast, okay. So normally it means that, for example, if the overshooting is allowed, okay, so normally this is the target. It means that you want a fast dying oscillation with a fast response, okay. So for example, imagine something like this. For example, if for example you have an option between, for example, something like this, okay, and something like this, you prefer something like this, because you see the rise time for this one is very slow, right? So it takes a very long time to reach, okay. even for example, if does not have any, for example, even imagine for example something like this one, something like this, right? But it does not have any oscillation at all, okay? So he just perfectly is critically damped, those kind of things, okay? Or for example, this one is critical. But if you see something like this one is still more okay. So what does it mean? It means that something like this still have faster rise time, okay? So although you have a, for example, oscillation or something like that, okay, but it dies fast, okay? This one is critically damped, for example, does not have any oscillation or whatsoever, okay? He just perfectly go there, but the fact is that it is slower, okay? So for fast application, this one is still this is still preferable. This is the reason that I say that you cannot to judge the things by its cover, okay? So you really have to see the end application and see what the customer wants, okay? So when you are doing the tuning, okay? So it is important. So two things is important, okay? You are far away from the real axis. The far away you have, for example, from the real axis, this one is X, okay? The far away you have your oscillation, as you can see, the frequency of your oscillation is different, okay? The second thing is that how close you are, for example, how right you are or left you are, okay? The left you are more stable. The right you are more unstable. If you are on the middle, you are oscillator. If you are on the right, what will happen to you is that you are unstable. You will blow out. Okay, so it's just matter of time. Okay, so yeah, so that's it. I will add this one to the original video. But I think it's enough for about the, for example, from the damping and for example stable, unstable, those kind of things. So all you need to remember is that if in certain regions you are unstable, on a very specific region, okay, this one is a specific region that I'm talking about. So you are an oscillator, and this one still has application. Oscillator has application, even in automation it has application. And in another region, okay, on the left side of the imaginary axis, you are totally stable. It means that you converge, okay, you will never, your oscillation will, it may take forever, but eventually will die, okay? May take a very, very, very long time, but it will definitely die, and he will settle on in a certain value. So this is the most important thing that you have to learn in this graph, and this is very important because this graph, what it teaches you is that if you do a big mistake, what will happen to you is that you can damage stuff. You have to know your target, and you have to understand these graphs, okay, to be able to tune, okay? So you have to know your objective. These graphs, it will tell you what would be your objective for tuning. This is very important, okay? So definitely go watch this video from the Richard Bolt, and thank you for watching. So in the next video, I will start to discuss about the PID tuning, KP, KI, KED, because we already have all the basics to know what to look for, okay, when we do the PID tuning. So in the next video, we can already start to discuss about it. Thank you and have a good day. Bye.